Welcome to Dr. Sherry's Astronomy channel. The theme this time is gravitational waves from merging supermassive black holes. According to Einstein's general theory of relativity, the presence of massive objects causes distortions in spacetime. Even if a massive celestial body is not in motion, the distorted spacetime can create gravitational lensing effects when observing background objects, resulting in multiple images or brightened observations. The most intense gravitational lensing effect is observed as an Einstein ring. Gravitational lensing can be observed through regular light, and it has been detected using advanced instruments such as the James Webb Space Telescope. On the other hand, when massive objects are in motion, the distortions in spacetime propagate as gravitational waves at the speed of light. Gravitational waves are believed to pass through everything without attenuation. The existence of gravitational waves was first proposed by Einstein in 1916, but it took almost 100 years to verify them through observation. Indirect evidence was obtained in 1974 through pulsar observations, but the first direct detection occurred in 2015. In September 2015, gravitational waves from the merger of two black holes, each about 30 times the mass of the Sun, were detected for the first time by the LIGO gravitational wave detector in the United States. Later, in 2017, gravitational waves from the merger of neutron stars were detected, and corresponding astronomical objects were identified through regular light observations. This discovery marked the beginning of multi-messenger astronomy, where multiple types of signals from the universe are used for observation. Gravitational waves, like light, have properties of waves, including wavelength and frequency. When the wavelength of gravitational waves changes, the astronomical phenomena observed are also affected. Ground-based gravitational wave detectors like LIGO detect high-energy waves with short wavelengths, which are comparable to X-rays in light. These waves can capture mergers of compact objects like black holes or neutron stars. Longer wavelength gravitational waves are also being studied through the European Space Agency's LISA, Laser Interferometer Space Antenna, mission. These longer wavelength waves are expected to detect the mergers of supermassive black holes or black holes swallowing stars. Moreover, even longer wavelengths could help observe phenomena like the inflationary period shortly after the Big Bang or the mergers of supermassive black holes. The universe is thought to have begun with a Big Bang 13.8 billion years ago, followed by a rapid expansion known as inflation. Inflation is considered a crucial origin for the structure of the universe as we know it today. On the other hand, the merger of supermassive black holes is considered essential for the growth of black holes as the universe evolves. It is believed that supermassive black holes did not exist at the time of the universe's birth, but many have been discovered in the nearby universe. Therefore, black holes have been growing along with the evolution of the universe, and mergers of black holes play a key role in this process. These phenomena cannot be observed directly with light. For inflation, the light from before this period is hidden by the cosmic microwave background radiation. Also, black holes do not emit light. Thus, gravitational wave observations are a vital tool for understanding these phenomena. Like light observations, detecting gravitational waves at different wavelengths requires different types of detectors. Let's first look at the principle behind detecting gravitational waves. The detection of gravitational waves relies on the fact that space itself stretches and shrinks. When a gravitational wave passes, it causes a tiny distortion in space, which we measure to detect the wave. For example, LIGO uses two long arms arranged at right angles. Each arm is several kilometers long. At the end of each arm is a mirror, and laser light is sent in and reflected back to travel back and forth along the arms. When the laser light returns, the light from both arms is made to interfere, and the timing and fluctuations in the light wave are measured. Changing the length of these arms changes the wavelength of the gravitational waves that can be detected. To observe intermediate wavelength waves that are difficult to detect with ground-based detectors, LISA will deploy multiple gravitational wave detectors in space. To detect even longer wavelength gravitational waves, a method has been developed to use neutron star pulsars as part of the apparatus. In this case, the length of the arm corresponds to the distance between Earth and the pulsar. This distance is measured in light years, making it very large. With such massive arms, ultra-low frequency gravitational waves in the nanohertz band can be detected. This technique is called the pulsar timing array. The millisecond pulsars used in this method rotate several hundred times per second. Like light from a lighthouse, light from a pulsar is observed at a constant interval. For example, this is how the light curve would look. These types of pulsars emit periodic pulses at various wavelengths of light. Thus, the light from pulsars acts like an incredibly accurate clock. If gravitational waves are arriving from all directions, the inherent distance between the pulsar and Earth will stretch and compress due to the waves, causing very slight shifts in the pulsar's pulse period. By measuring these shifts in pulse periods with multiple radio telescopes on the ground, we can detect gravitational waves. These radio telescopes are used for observing not only pulsars but also various other celestial objects. The number of millisecond pulsars has been increasing due to observations across various wavelengths in recent years. For example, the number increased dramatically through all-sky gamma-ray observations by NASA's Fermi satellite. In 2023, the first measurement of background gravitational waves used 68 celestial bodies. In other words, while ground-based gravitational wave detectors have only 2 arms, using 68 arms allows the measurement of the distortions in spacetime caused by gravitational waves. This figure shows the angular separations and correlations between pairs of pulsars measured from 67 pulsar arrays, consisting of 2,211 pairs. The blue points represent the actual data collected. The black dashed line represents the pattern predicted by Einstein's general theory of relativity, showing the expected pattern of background gravitational waves from all directions in the universe. The measured data closely matches the model, confirming the presence of background gravitational waves. Recently, the Meerkat pulsar timing array has increased the number of pulsars to 83, creating an intensity map of gravitational waves across the entire sky. Here is the actual map. The white stars show the positions of the observed pulsars. The size of each star relates to the timing precision of the pulsar, with smaller stars indicating less error and larger ones indicating more significant errors. The areas with stronger gravitational wave intensity are shown brighter. Looking at the intensity map, one region stands out as much stronger than the others. Inflation right after the Big Bang is expected to show isotropic intensity, so this pattern suggests a different origin. Therefore, it's highly likely that this strong signal comes from mergers of giant black hole binaries. Recent observations with the James Webb Space Telescope have also detected indirect evidence of giant black hole binaries. The uneven distribution seen in this gravitational wave map is crucial as direct evidence of such black hole pairs. However, the reliability of the intensity map's unevenness still needs further confirmation. Ongoing observations are expected to provide more conclusive evidence. The future developments are certainly exciting. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.